We've now looked at the trig functions, so now we're going to look at sketching them. In any situation with any function, if we don't actually know what shape our function is, what we do is we draw up a table of values and then put some points. Once we know what it looks like, then we stop plotting and we just start sketching. So if we use the angles that we've got here and we use our calculator to find the sine of 0, 0, a half, 0.866, 1, 0.866, 0.5, 0. When theta is 210, it's negative a half, and it's negative 0.866, and it's negative 1, negative 0.866, negative a half, and 0. And remember that adding or subtracting 360 doesn't do anything, so we could actually continue the graphs this way or that way as well. So let's draw sine on the vertical, theta there, sine theta, and let's mark off 90, 180, 270, 360, and divide that in 3. So now we've got the same gaps as we had before, and we need 0.5. And we need 0.866. And we need negative 0.5, negative 1, and negative 0.866. Okay, now we just plot on the pieces. At 30, it's 0.5. At 60, it's 0.866. At 90, it's 1. Coming down. And if we carefully join those together, we get a sine curve. So this is the graph of y equals sine theta. Now, it doesn't stop at 360. The top curve here is showing the sine curve where it's going as far to the right as we choose, or as far to the left, and it just repeats itself over and over. Now, we could do the same process for a cosine curve. We could draw ourselves a table of values and then we could plot them, and we'd see then that the cosine curve starts at 1 when theta is 0. Otherwise, it's kind of the same. Have a look at it. The top one's the sine curve, the bottom one's the cos curve. The only difference is a sideways shift of 90 degrees. And that's something that we're going to be looking at shortly, is this idea of a sideways shift. Similarly, we could plot a tan curve, and remembering that at 90 degrees, tan is infinite, so in actual fact there's a gap in there, and the same then at 270. And repeating as long as we We know that the sine and the cosine curve repeat every 360 degrees or every 2 pi radians. So we talk about the period. The period is the time that it takes to go right round, like that. So that would be the period from start to end of one cycle. So if we're talking about the sine and the cosine curves, we say that the period of those would be 360 degrees or 2 pi. Now, just having y equals sine x isn't going to be enough. We need to have something a little bit more elaborate. We need to have y equals sine, or a sine some sort of number before the x, and in actual fact we can go really fancy and have it plus something else, doesn't matter what you call it, like that. The first graph on this page, look at it, it's still going up to 1, but this time instead of going round in 360, it's actually going round in 180. So it's going round twice as fast. So we talk about the period for this one being pi, or 180 degrees. And it's going around twice as fast, so we would name it as sine 2 theta. The second graph on the page is still going up to 1 and down to -1, but if you have a look at it, it's going around once, twice, 3 times in 360. So the period for that, the time period for that is going to be 2 pi divided by 3, or 360 divided by 3. Now it's going around 3 times as fast, so we would write the equation as y is equal to sine 3a. If we didn't know what it looked like, we would fill in a table of values. We'd find theta, we'd find 2 theta, then we'd find sine of 2 theta, and then we would actually plot it. What we should have seen is that sine 2a has the same general shape as sine of a, but it's going around twice as fast. So in this case, one cycle will be completed in 360 over 2 degrees, so that's 180 degrees, or 2 pi over 2 radians, pi radians. So generally what we're saying is that the period is 2 pi over k, and we're getting that k from there. So the period is 2 pi over k. It completes a cycle every 360 over k. Actually, that's not right. It completes a cycle every 360 over k degrees, or every 2 pi over k radians. And another way of thinking of that is that it completes k cycles every 360. So sine 2a completes 2 cycles every 360 degrees. Graph number 1. Graph number 1, it's going up to 3 this time, so it's got a vertical stretch, if you like, of 3. It's still going around twice as fast, so we would rewrite the name of it. We would call it 3 sine 2a. Graph number 2, It's going up to 4 and down to -4. It's a cos curve. It's going twice round in 360, so that we would say that its equation is y equals 4 cos 2x. Graph number 3 is interesting. It's not even going round once in 360. In fact, it doesn't go round once until it's been to 600. It's actually going round 3/5 as fast. So it's going around 3/5 as fast, and it's stretched vertically by a factor of 2. So we can make graphs go around faster, and we can stretch them vertically, but we can also shift them. Think about what would happen here if we shifted this curve. If we looked at y equals cos theta plus 30, what we need to do is find theta plus 30 and then find the cosine of each of it. What we actually find is that it's shifted the cos curve to the left. So there's our cos curve. And by adding it, it shifts it a little bit to the left. So this point is now over here. This point is now over here. This point is now over here. This point is now over here, etc. Like that. So it's moved that way 30 degrees. We talk about that shift as the phase angle, or the phase shift. And it's gone to the left. If it's important to us, particularly the electrical people, what we'd say was that this leads by 30. It starts sooner. It's starting here as opposed to here. So it starts sooner. It starts earlier. That's how I remember it. It's EA. It starts earlier. It's the beautiful version of the curve. It's moved to the left by 30 degrees. We may well, though, want to have time on the horizontal, in which case we're then saying that the currents, etc., are varying with time. And if our curve is y equals sine t, then the period is said to be 2 pi seconds. This is the amplitude, and this number, previously we were calling it k, but it doesn't really matter. This is omega, and we talk about it as being the angular frequency or the angular velocity. Omega would have units of radians per second, and omega t would just have units of radians, because it would be radians per second times seconds. Question's easy here. It's asking for the angular frequency of each of the functions. Number 1, the angular frequency is 3 radians per second. Number 2, the angular frequency or the angular velocity is half a radian per second. And for the third one, the angular velocity is 2/3 of a radian per second. Question 1, omega is 6, so the time period, the time it takes to repeat, is 2 pi over 6, or pi over 3, and that'll be in seconds. Question number 2. In this case, omega is pi, so put it out here. T is equal to 2 pi over pi, which is just 2. So it repeats itself every 2 seconds. For number 3, omega is 100 pi. So the time period is 2 pi over 100 pi, and we'll write that as a decimal. Now sometimes it might actually be better to write that instead of 0.02 seconds, it might be read better, and we'll see, to write that as 20 milliseconds. Now, what if we're given the other information? What if we're working backwards? The amplitude is 3 and a full cycle is completed in 4 seconds. So omega must be equal to 2 pi over 4, which is pi by 2. So putting that together, y is equal to 3 sine pi over 2 t. The last part, the amplitude is 4.2 and a full cycle is completed in 6 seconds. So that means that omega is 2 pi over 6, which is pi over 3. So our expression is going to be 4.2 sine pi over 3 t. Now sometimes you'll see this written as 4.2 sine pi t over 3. It's exactly the same thing, only here it's easier to spot omega because there it is there, but it's the same thing. The frequency, now this is not to be confused with the angular frequency. This is the linear frequency. It's the number of cycles completed in 1 second and it's measured in hertz. So if we look at just an ordinary straightforward y equals sine omega t, the time period is equal to 2 pi over omega. So 1 cycle is completed in 2 pi over omega seconds. So omega cycles completed in 2 pi. So using a bit of algebra, omega over 2 pi cycles are completed in 1 second. Now we've said that the number of cycles completed in a second is the frequency, so we can see from that that t is equal to 1 over f, or f is equal to 1 over t, and it'll be measured in hertz. I realise the graph is there, but let's have a look at how I came by that graph. The amplitude is 340. So the curve is going to go up to 340 and down to negative 340. Now what I like to do is I like to draw in the unshifted curve. So this is the dotted line first. So we're going to draw in the dotted line first. We need to find the time period. The time period is going to be 2 pi over omega, and omega is 50 pi. That's a 25th of a second, or we can convert it to milliseconds. We need to divide 40 into 4, so 10, 20, 30, 40, and draw in our unshifted sine curve so that at 10 it's 340, at 20 it's 0, at 30 it's negative 340, and at 40 it's 0 again. Now we need to dot that in, and now we need to move it. We need to find the time displacement, let's call it phi, because we're plotting against time. And it's going to be the opposite, because we were going to the left when it said positive before, over omega. And in this case, it's going to be negative of negative 0.541 over omega, which is 50 pi. And work that out, that's going to be at 3.44 milliseconds. So the graph is going to move, it's negative, negative, so the curve is going to move to the right by 3.44 milliseconds. That means that every single point is going to be 3.44 milliseconds to the right. Okay, so the peak of this shifted curve is going to occur 3.44 milliseconds after the peak of the unshifted one. Now the peak is going to be, instead of at 10, it'll be 10 plus 3.44, just 13.44, and the trough will be, instead of being at 30, it'll be at 30 plus 3.44, and the 0 will be not at 0 anymore, but it'll be crossing the horizontal axis at 3.44 and 40 plus 3.44. We could rearrange our y equals a sine omega t plus alpha. We could take out a common factor of alpha, and sometimes you'll see that it's written like this. And this bit here is what's giving you your time shift. So alpha is your phase angle, and because it's time, it'll be in radians, and alpha over omega is, as we said before, the time shift or the time displacement. The curve that we're looking at here, y equals 340 sine 50 pi t minus 0.54, is lagging the unshifted curve because it starts later. So it lags. This is a common exam question. You're given the alternating current. So find the amplitude. The amplitude is going to be 30 amps. The periodic time is going to be 2 pi over 100 pi. Or 0.02 seconds or 20 milliseconds, and the frequency would be 1 over that, which would be 50 Hertz. The phase angle is pi by 6, but you're asked to give it in degrees, whereas pi by 6 is clearly in radians. So pi by 6 in degrees would be 30 degrees. Questions like this are written in words. You've got to take out what you need. It states that the maximum displacement is 5. So if we think about that as being the hypotenuse, oops, did I say a right angle triangle? So that's the maximum displacement. And it says when time is 0, the displacement is 2.5. So when it starts, the displacement is 2.5. So you have a rotor arm, if you like, on the flat. When it starts, it's already gone 2.5 meters. And you're asked to express the displacement in the form y equals a sine something or other, plus or minus something. Okay, so we've got that a is 5, that's easy, that's the amplitude. And then the angular velocity, omega, is going to be 2 pi times f. And we're told that f is 50, so it would be 2 pi times 50, which would be 100 pi. Now, this is the tricky bit. The phase angle, well, we can work it out. What information have we got? We've got that sine phi, or some other letter, is going to be 2.5 over 5, if we put phi there. So we can work out that phi is equal to the inverse sine of 2.5 over 5. 2.5 over 5 is a half. The inverse sine of a half is 30 degrees. Or probably we should have it in radians. So our equation then is 5 sine 100 pi t plus pi over 6. And remember, if you've got t, then your phase angle needs to be in radians. We're asked to sketch one cycle. Right, we worked out that the time period was 20 milliseconds. And so let's draw the unshifted one. So it went up to 5 and down to -5. So 20, we need to divide that in 4. I'm just going to dot this one in. Like that. That's our unshifted curve. Now I need to find the phase time. So it's alpha over omega, which would be, from the previous page, pi over 6 over 100 pi. And we work that out. That will be 1.66 milliseconds. So the curve is actually going to move to the left by 1.667 milliseconds. So instead of being at 0, it'll start there. Instead of being at 5, it'll be about there. Instead of being 10, it'll be about there. Instead of 15, it'll be about there. Instead of 20, it's about there. And all we have to do is join it up. So the red one now, we really need to find that point there. We need to find where it cuts the axis. In any of these graphs, remember, it's going to cut the vertical axis where t is equal to 0. So we can just put that into the equation and we get that t is equal to, actually, it'll cut the t-axis. No, t is equal to 0, so it'll cut the y-axis when y is equal to 5 times sine pi by 6, which is sine times sine of pi by 6 is a half. 5 times a half is 2.5. So it'll cut the vertical axis at 2.5. Number 1, it's the time displacement is going to be 12 over 3, and it's going to move to the left by 4 seconds. The second one is going to move to the right. The curve is going to be redrawn to the right by 6 over 4 seconds, and the third one is going to be moved to the right by 2 over 0.5, which would be 4. Back in the days, we would have learned these trigonometric identities. Most of them you can prove from Pythagoras' theorem. You probably need to know best where to look them up. Now, there are some obviously that are going to be more important than others. Number 3, number 2, that's going to be important. That first one's important. That one's going to be important. We're going to use that one at some stage. And that's an important one. The first one there you can see definitely comes from Pythagoras' theorem. And the second to last one and the last one, when we come to do calculus, when we come to do integration, we use those last two a lot. So yeah, it would be really good if you learned them. Otherwise, you need to know that they need to be in your formula sheet that you're going to look them up.